Hello, I'm Mike Dudley with the Virginia Asphalt Association. I'm going to go through some of the evaluation of your design blend for the mix design class. Through this, we're going to talk about the furnace correction factor, a permeability test, and even though it's not required as part of your mix design, we will discuss TSR tests. To begin with, we'll talk about the furnace correction factor. It's for your asphalt content and gradation. This procedure, we follow VTM 102. The furnace mixture calibration is a required part of the approval process for all mix designs in VDOT. The testing temperature for this test is 538 degrees Celsius. I think the majority of the state does use that temperature. But if you have a really high correction factor or something that would cause your correction factor to be high, which is a large breakdown in aggregate, you do have the right, and I would actually suggest, because your test results will be more consistent, that you test at a lower temperature, 482 degrees Celsius. That is an approved alternate test temperature for any aggregate that has high breakdown or a real high correction factor for your furnace correction factor. To do your furnace correction factor, you have to prepare 4 individual calibration specimens that will be mixed at optimum asphalt content. These 4 samples have to be batched and prepared individually. We can't have one large sample that we're splitting down. The materials we use to create these samples, to build these samples, both the aggregate wrap has to be from the current construction season. It can't be old materials been sitting in the lab for a while. It has to be this fresh produced product. And when we're making these individual samples, there's one more sample that's required, and that's a blank sample for the gradation. And the reason we batch and do a blank sample is for gradation comparison for the 4 that we actually burn. The blank is not burned. Let's talk about sample size. You'll find this table in the VTM, and there is a minimum sample weight for each, depending on the aggregate size of your mix. There is a minimum sample weight, as you can see here. But one thing I also want to note to you, there's also a maximum sample weight. The maximum sample weight would be 500 grams greater than the minimum. So if we're dealing with an SM 9.5, the minimum is 1,200 grams. The maximum would be 500 more, which is 1,700 grams. Your samples have to be within that range. And now, all your samples that you're doing your furnace correction factor with should be similar to the sample weight you're going to use when you're actually doing field production. Sample weight can impact these test results, so you want to keep that as constant as we can. Let's talk about managing wrap for this procedure. This is one place I see people do things a little differently. When we batch up our aggregate samples, we all have batch pans, we all batch our aggregate up, but when it comes to wrap, we're not supposed to scoop wrap, especially when you're dealing with your furnace correction factor. All wrap material should be split down. All right, what I'm saying is, we're going into mix design season. Mix design season for us is the winter months. We should get a very large sample of wrap. I would suggest you get a very large sample of all your materials. I'd get a loader bucket dumped out beside my lab of each quantity of material I have on my yard, and that's what I will do, go back and forth to get samples so it stays consistent the entire time I'm doing my mix designs. But I need to get a couple bags at least of wrap, and I need to oven dry the wrap. It needs to be to a constant weight. And that's so that nothing changes while I'm working through this process. As I was saying before, all wrap must be divided using a sample splitter. We all have sample splitters in our lab. I don't have a picture up here, but we all have them. When you're trying to prepare your aggregate and wrap materials to be mixed, you can scoop your aggregate, but your wrap you should split through a splitter. And I know you're not going to get the exact gram. But now, the scooping that was required in the wrap will be minimized to a very small quantity versus it being, especially if we're running a mix that's got 30% wrap or more. That's 30% of the material that when we scoop wrap out of a pan, we can really affect the asphalt content that's coming out of that wrap. So we want to split it through an aggregate splitter, and then we only want to scoop, 50 grams or here, a smaller quantity, versus the large amount to get the exact weight we need for our batch samples. Our batch weights for both our liquid, how much virgin liquid we're going to put into our furnace correction factor sample, we need to know how much liquid is in our wrap. To do that, we burn 4 wrap-only samples to determine the AC from the wrap. For this, when we obtain these wrap samples, we should obtain these samples by splitting. And we should follow the same test minimum weights that I showed previously. You back up here. These same weights should apply for our wrap-only burns. If we're dealing with if we've sieved our wrap and we've fractionated our wrap over a 12.5 sieve, then we want our wrap burns to be between 1,500 grams and 2,000 grams. All right, so that rule applies even for wrap-only burns. With that, so now let's talk about it. We got our samples down, we've split our wrap samples down, and we're ready to do our furnace burns on wrap only to establish how much AC is in our wrap. When we're burning these wrap samples, we want to burn them with a 0.40 correction factor. This is a requirement in Virginia. It's required by the VDOT specifications. Okay? So all wrap-only burns, and I want to clarify that, wrap-only are burned with a 0.40 correction factor. Once you burn your 4 wrap samples to obtain the amount of asphalt content that's in your wrap, you have the aggregate that's left from each one. I recommend taking a couple of those samples, and I can do a gradation on them. That would give me my materials for my F&E on the coarse side, and it would give me my aggregate for my fine aggregate angularity. Both tests are required to be reported on your wrap material. I take the other 2 samples and use that material when I'm batching up my blank gradation for comparison to my furnace correction factor samples as I burn them in the future. All right, and one other thing I would recommend, when I'm splitting down, this is extra here, this isn't necessarily part of managing wrap for your furnace correction factor, but as an extra here, we also need to know the effective specific gravity of our wrap, which will be used in our mix design calculations. The fact that I had a very large sample, approximately 80 pounds of material of wrap that came into my lab and was mixed properly and has been used for all this other testing, I would go ahead and split out a couple samples and run a rice on the wrap for 2 samples, average those 2 rices so I can then calculate the effective specific gravity of my material. All right, back to VTM 102 procedure. When we're actually doing the VTM 102, which is to establish a correction factor for our mixes, that specification tells us we need to batch 6 specimens. Let me explain where I'm coming up with 6 specimens. It requires that we batch a butter. We do discard that butter, but the specification calls that we batch a butter, mix it in our bowl. So that bowl has been buttered with the proper AC, and assuming all cleaning procedures stay constant, that there's no aged AC in there or anything that will affect our first furnace burn. So we are to batch and mix a butter and discard of that. After that, we need to batch and mix for mixing 4 specimens that we're in turn are going to do our furnace correction factor with here in a minute. And this is the blank sample you've heard me referring to. The specification requires we batch a blank, which is aggregate only specimen, for gradation comparison. This comparison will go back and compare to the 4 gradation specimens, the 4 burn specimens we do a gradation on. Okay? Now, understand if you're batching round numbers, 1,500 grams for test specimens, I need to make sure that the aggregate only, because a lot of this, the wrap weight would have AC in it, this sample would be smaller than my mixed samples, because I can't put 1,500 grams of the wrap aggregate, I can't put a proportion of the wrap aggregate equal when I don't have the liquid in it as I do when I do have the liquid in the wrap. So you would almost have a separate batch sheet, or a separate blend sheet for this one sample. All right, I think I've mentioned it already, but I'll say it again. Specimen weights for these target correction factor samples should be similar to what we're going to separate and do during production for the year. Specimens can be mixed and placed directly into baskets. That is an option for us if we chose to do that. It's not required. You can also mix them and put them in a pan. You do not have to oven condition these samples. If you put them in a pan and allow them to cool off, you need to preheat them in an oven at 125 C 257F, which is an odd number, for 25 minutes, but we don't put the baskets in the oven. We only preheat our sample and then charge the basket the same as we would if we would have mixed them and put them directly in the basket. What you find happens is you got to do 4 of these. Most of us don't have 4 sets of baskets sitting around. So the first one we mix, we'll put in the basket, we'll put it in the furnace. While that furnace is burning, we go ahead and mix the second, third, and fourth, and we allow them to cool off, but we have to preheat them again before we put each one in the basket, okay? When we actually burn our furnace correction factor samples, this is the only time we set the ignition furnace with a 0.0 correction factor. The whole purpose of what we're doing here is to establish the difference in a known asphalt content that we mix these samples at versus the measured asphalt content that comes out of the furnace. That is how we determine the furnace correction factor. We've burned 4 samples, so you got test 1, test 2, test 3, test 4. What we want to do is average these up, so we add them together, divide by 4, and this average is actually our furnace correction factor or our mixture calibration average for this particular job mix formula. One note here, when we do these 4 tests, if any 2 burns exceeds more than a 0.15%, so in other words, if there's more than 0.15 difference in any of the 2 samples, you discard the highest and lowest result and only average the remaining 2. I would recommend, if that's the case, you got that much variability in your furnace correction factor calibration, I would recommend going back and either doing the whole process over or at least doing 2 more samples. I think that's a little bit more accurate than just discarding the 2. You're going to use this furnace correction factor for our entire paving season unless something gets fishy. So we want to have good confidence in our number that we're using. Once we finish the actual burn process to establish our furnace correction factor, we have to do a gradation on all 4 burns. I'm not going to go into a lot of detail on the gradation process. That's already been taught to everyone in the mix design class when they went through the Plant 2 certification course. There are a couple things I want to point out that I see continuously overlooked is we want to make sure our sieving time is sufficient. When I talk about your sieving time being sufficient, we're all, I don't know if the word's programmed to sieve for 10 minutes, but not all sieving apparatuses are the same. There is a procedure in there is a process in AASHTO T30 that explains how you determine for your particular sieving apparatus if you're performing a sufficient enough sieving time. And that is to basically, once in a while when you calibrate your sieves, you need to make sure that if you handshake each sieve for 60 seconds and less than 0.5% of material comes from passes that sieve, then the sieving time you are using is sufficient. I know the old, very popular sieve shaker nowadays is the Marianne, or it's a device that sort of leans back at an angle and it's a rotary shaker. And I've used those for 20 plus years, and I found that to meet a proper sieve time, I had to usually run about 13 minutes instead of 10 minutes, just due to the different process and how it does its sieving. One other thing I want to talk about is not to overload any sieve. This is probably one of Mike's pet peeves, because when I spent some time in the past working in the lab, I saw this overlooked continuously. There is a limit of amount of material that can be retained on any one sieve. And if you're dealing with 8-inch sieves, this is a very typical gradation for an SM 9.5. And you can see the sample weight is a very typical sample weight. He had his aggregate before he washed it was 1,485 grams. That's very typical sample size. After he washed it, he has 1,391 grams. All right, in his sieving process on the number 4 sieve, he had 507.6 grams retained. For an 8-inch sieve, the maximum weight he can have on a number 4 sieve is 330 grams. He did nothing wrong with his process. He sieved it. He's done all the work he had to do his gradation, but he's overloaded this sieve. what's probably going to happen here is he's got an error in his actual, when he calculates out here to his percent passing, there'll be a small error in his calculation because this sieve was overloaded. So it's important that we look in AASHTO 30, T30, and make sure that we're following the correct processes here. Here's a quick demo. All right, here's his furnace correction factor sample he's mixed up. He's got 1,654 grams. Here he is getting ready to load his baskets. Baskets are on the scale. He's tearing them off. He's going to load half his sample in the bottom basket. Going to spread it out nice and uniformly. He wants to keep about a ½ inch all the way around the outside so none of the material falls out of the basket. He wants everything to stay, while his sample is burning, he wants everything to stay inside the basket. That's a good example of just spreading the sample out. Puts his second basket on top. Puts the remainder of his furnace correction factor sample in the top basket. He spread that out just like he did the first basket. Puts the lid on, and he's got 1,652.6. So when it comes to putting his sample in the furnace, there's no decimal point available. He'll be putting in 1,653 grams. Here he's checking the total weight of his baskets just to make sure when he loads his baskets in his furnace, he's not touching the side. Here he's putting his sample weight in. Enter. Checks his weight, it's right here, 1,653. Here he is loading the furnace, placing his sample in the center of the furnace baskets, and he's making sure this weight was within 5 grams of his combined weight that we had when he weighed the basket and his sample. His sample has completely burned. Here's his burn ticket, it automatic comes out, says his sample's done, and now he's ready to remove his sample from the furnace. All right, now that we've completed the furnace correction factor, we're going to talk about permeability test. The test procedure for that test is VTM 120. Permeability test is a test that's required to be done during the mix design phase. It provides an indication of the water permeability of a water-saturated sample of a compacted mix. All right, this measurement is to measure how easily water will be able to move through the air void structure of the mixture while it is placed and under traffic in a compacted state. It's an indication of the interconnectivity of the air voids in the mixture at a given density or void content. Like I was saying, the permeability is measured during the mix design process. We've done enough permeability testing now that we know its permeability is pretty much a direct function of the gradation of your mixture and the void content of your mixture. To do this, we use a falling head permeameter test to determine the ratio of flow of water through a saturated specimen. And specimens have to be compacted to a specific void content and to a specific height. Here's a table from VTM 120, and depending on the nominal maximum aggregate size of your mixture will determine how tall your specimen needs to be. Acceptable permeability must be less than 150 times 10 to the minus 5 centimeters per second, which is the flow rate of the water at 7.5% air voids for your specimens. There are 2 methods for testing and evaluating the permeability of a mix design. One is the regression method. The regression method is basically you make 3 sets of peels with 3 specimens per each set. So that's a total of 9 specimens. There needs to be a void range between those specimens ranging between 50 times 10 to the minus 5 centimeters per second to 500 times 10 to the 5 centimeters per second. All right, for the single point check, you need to make 5 specimens with a void content equal or greater than 7.5%. And the range of voids for the individual specimens should be equal to or less than 1%. Basically what that's saying is if you start at 7.5, your voids can only go up to 8.5%, and that range has to encompass all 5 of your specimens. To do this, we're going to be saturating the specimen before we do any testing. To saturate our specimens, we vacuum them at 90 millimeters of mercury for 15 plus or minus 2 minutes. And after vacuuming, once you vacuumed your sample, it has to remain in water with no agitation, with anything going on, for a minimum of 5 minutes before you can do your permeability test. What I've seen done a lot is you'll vacuum saturate all your samples that you're going to test at one time and just set them over in your wave bath. So once you start running a permeability test, you don't have to keep switching back and forth from saturation to permeability testing. Because they can sit in there for a minimum of 5 minutes, but they can sit there longer. Nothing's changing in the specimen while it's sitting in water. And here's a short video of how the vacuum saturation process works. All right, here the technician is putting a spacer in the bottom of his rice bucket. He's using his rice bucket to saturate his specimen. His specimen's laid on that spacer. It cannot lay flat on the bottom of the bucket. He's adding his water. This water should be at room temperature. Typically this water comes out of his wave bath at 77 degrees. Okay, now he's going to take his bucket and he's placing it on his shaker here. It's not to have any agitation during the vacuum process. That's just how the lid to his bucket is fastened on. When he actually turns on the vacuum, the shaker has been turned off, so it's no agitation during this 15 minutes. Now he's getting ready to start the vacuum, and here's the manometer getting down to the proper manometer reading, vacuum pressure. Here's a diagram of the actual permeability apparatus. A couple pictures here. It's a falling head permeameter. As you can see from the first picture here on the right, water flows through the tube, the graduated cylinder. It comes and disperses across the top of your specimen. It flows vertically straight down through the specimen and comes out the bottom. And all you're going to be doing is measuring the water flow through there. Here's another diagram come out of the specification. This is actually showing us a little bit more about the angle of how the water is allowed to go and cover the entire surface of the sample, and the entire surface is allowed to exit at the bottom. Your exit tube coming out the bottom here on the left diagram, this exit tube, the bottom of the pipe must be equal to the bottom of your specimen. When you order permeameters, these pipes are not attached. And part of the specification requires that when you attach these exit pipes, that you get the bottom exit equal to the bottom of your specimen. All right, for lab specimens, you apply a thin layer of petroleum jelly to the sides of the specimen, and this is to assure a good seal between the specimen and the membrane. We want all the water to flow through your sample, through your specimen, and not around the outside. We're going to apply a confining pressure of 14 plus or minus 1 psi during this testing. There again, that's to assure the water flows through the specimen. We're going to fill the graduated cylinder with water to begin testing. The water we're actually going to use to run our permeability samples with has to be prepared a little bit. What has to happen for that is the water should have been kept at room temperature for at least 12 hours. There's a couple reasons for this. Most faucets have an aerator on the end of them. You do not want this water to be aerated. So one, you need to draw a couple 5-gallon buckets of plain tap water. You can use tap water for the test, but this tap water should be left on the counter overnight so that it's well de-aired. The air's had time to evaporate out. And two, the water's now at a constant temperature during your test. Both temperature and aeration can impact the results of permeability testing. So once we begin running our test on our actual specimen, we're going to record the time it takes for the water to flow from the upper to lower timing marks. There's 2 marks on your graduated, on your on your tube, and it's basically a top mark and a bottom mark. This is pre-calibrated, and you just need to know how long it takes the water to flow between those two marks. We're going to continue until we have 3 consecutive measurements that are within 10% of each other. Typically, that's not much more than 3 or 4 runs. If it takes more than 3 or 4 runs to get that, you probably are having some sort of leak in your permeameter apparatus and how you were sealing everything, and you may end up having to discard that sample and just run another sample. Once we've got those 3 consecutive readings within 10% of each other, we're going to average the 3 and report 1 permeability value for that particular specimen. This is a big formula, a lot of explanation here. It's in the test procedure. You do not have to know it, memorize it, nothing like that. You have the test procedure in front of you. Here's a nice diagram of somebody who done the regression method. As you can see, they had 3 samples with an air void structure of around 7, 3 at around 8.5, and 3 at around 9.5. And from that, they were able to do a nice plot and show the permeability. What this plot will tell us is that to meet permeability, we have to have a maximum of 150 times 10 to the minus 5 centimeters per second. So based on that void structure we have, I'd say about 8.3% air voids. Anything below that would pass permeability. Anything above that would fail permeability. Here's just an image of a picture of the actual apparatus in a laboratory. All right, here he is. The technician is applying the petroleum jelly to the sides to prevent any leakage, create a good seal, loading the collar over top. I'm going to apply confining pressure. And then he's testing his sample, just a standard stopwatch to determine how long it takes for the water to pass between marks. If you look up here at the top, that's his bottom mark. That white mark on his tube there is his bottom test mark. Here is a demo video to show how this works. All right, the technician is applying the Vaseline to the outside circumference of his sample. You do not want any on the top or bottom. That would impede the water flow. Now what he's doing here is the vacuum that he's applying now is to make it so that the rubber membrane is pressed out against the sides of the collar. The collar is slid over top of the specimen. He's putting the top plate on his actual specimen, and he's going to bolt it into place and secure it nice and tight. Tighten it down. He's reinstalling his cylindrical tube. Now he's applying his confining pressure. You see a nice image of the pressure gauge. So he's got to be within 14 plus or minus 1 psi. Now he's filling the tube up with his water that's at room temperature for at least 12 hours. It's de-aired. It's been allowed to de-air. You can see that top mark is about 63 centimeters. What he's doing now is he tilts it back and forth. You saw that bubble come out? That's to make sure there's no air trapped on the top of the specimen, which would impede the permeability test. So he just does that a few times before he actually runs the test. There went one more bubble. Now he's going to allow the water to start flowing, and he starts his timer once the water in the tube hits the top mark, and he'll stop it once it passes the bottom. Next test we're going to talk about is TSR, or a stripping test. For this, we follow AASHTO T283 test procedure. AASHTO T283 is a test method that can be used to determine if materials, the aggregate and binder, basically, are subject to stripping and measure the effectiveness of certain additives. In Virginia, we're allowed to use either hydrated lime or a chemical antistrip. And in Virginia, we mandate the use of an antistrip additive in all our mixes. We found that that's sort of a good insurance policy that assures us we get good performing mixes as far as stripping would be impacted. To do this, we need to prepare plant mix samples. TSRs are, as of 2018, TSRs are no longer required as part of the mix design process. TSRs are to be performed at beginning of each construction season or each calendar year, if you want to say, and it needs to be performed on plant-produced material, and all TSRs need to be started within the first lot. The reason I say started within the first lot of a new mix production is the TSRs, you're going to find out, some multi-day tests, and depending on your startup, you may finish the first lot before you're done the TSR test, but you have to have at least started performing the TSR test on your material for this particular mix. All right, so as I'm saying here, your material is plant mixed, but lab compacted specimens. In order to run the TSR test, you need a minimum of 6 specimens, but as you can see here, I recommend 8 or more. You'll find out real quick why I recommend the extra samples. Specimen size is purely at the technician's discretion. If he wants to use 4-inch or 6-inch, 4-inch can be used. If you're doing 4-inch, typically that's a Marshall-made sample. 6-inch is a gyratory-made sample. If you're doing base mixes, though, we have to run the 6-inch sample because of the aggregate size. Prior to making our samples, we want to make sure our mix is at compaction temperature. That helps assure a consistent compactive effort. And we want to compact our specimens, whether it's being with the Marshall hammer or the gyratory, to 7 plus or minus 0.5% air void content. Here's the first reason I recommend you make a few extra samples when you're preparing your samples. You're not going to know the void content of your specimens till after you've had a chance to bulk them. And if you only made 6 and a few of your samples are not within 7 plus or minus 0.5%, now you don't have enough test samples to run your tests, and you have to go out and get more samples. So I recommend always making more than a minimum of 6. All right, once I've made my specimens and measured the air void content, they need to be stored at room temperature for 24 hours. Okay, it's important that they're stored for 24 plus or minus 3 hours. They need that time. Once we've done that, we want to separate our samples into 2 subsets of at least 3 specimens each. 2 times 3, that gives us our 6 samples with approximately equal air voids. What we're saying here is we don't want all the low air void content to be in one set and all the high air void content to be in the other. We want the average air void content of the 3 specimens in each subset to be as equal as you can get it, or equivalent as you can get it. All right, the dry subset. We're going to have a dry subset and a conditioned subset. The dry subset, those specimens are stored on a shelf until the other set's ready. I recommend maybe laying a cloth or a piece of paper over them. Just let them sit there so nobody messes with them. The conditioned subset. The conditioned subset, we first got to vacuum saturate these specimens to between 70 and 80% saturation. Notice the narrow saturation range, 70 to 80%. The catch here is, though, if we go above 80%, the specimen has to be discarded. If it's under 70%, we can apply more vacuum saturation until we get in between the range. But if we go too far, it has to be discarded. Here's again the reason I recommend we have a couple extra samples until we get beyond this point. Okay? One thing I will tell you too, if you oversaturate your sample, all you're going to do is hurt your TSR value. So it's very important that it be discarded and not tried to, oh, I can make this sample work, it just barely went over. All it's going to do is hurt your TSR result. So it's to everyone's benefit to discard it if it goes above 80% saturation. This range used to be much larger. It used to be between 55 and 80, and it was funny. If you were a producer, all your samples were between 55 and 65, but if you were with the state, all your samples were between 70 and 80. So now the specification's been changed. Everybody wants to do it the same. All saturation needs to be between 70 and 80%. All right, once the samples have been vacuum saturated, you wrap each specimen with saran wrap and place it in a plastic bag with 10 milliliters of water. All right. After we've done that, the samples are placed in a freezer for a minimum of 16 hours. Specification just says minimum 16 hours. If you leave it there for 24 just because you start in the morning and you're going to finish the next, you pick it back up the next morning, that's perfectly fine, but it needs to be at least 16 hours. After they come out of the freezer, they've been frozen for 16 hours, they're placed in a hot water bath, which is 60 C or 140 degrees Fahrenheit, for 24 plus or minus 1 hour. Now, remember these samples were wrapped in saran wrap and in a bag. When we place them in this hot water bath, we remove the bag and we remove the saran wrap. So these specimens, as you see in this image here, do not have any wrapping on them. They're just sitting in the water bath at 140 degrees for 24 plus or minus 1 hour. Now, after that 24-hour soak in the hot water bath, the two subsets can come back together. When they come back together, we're going to place them in a second water bath at 25 C or 77 degrees Fahrenheit for 2 hours, plus or minus 10 minutes. We don't want them left in there much different than 2 hours. Okay? The dry subset, we don't want them to get wet at all. The dry subset should be wrapped with the saran wrap just as the previous set was and placed in a leak-proof plastic bag. Now, all 6 samples should actually be in the water bath at the same time for that 2 hours so that all are subject to any kind of temperature fluctuations continuously at the same time. And it is definitely recommended that when you add these hot specimens to your water bath temperature is going to rise, and you don't want that. So it's recommended that you add some ice. You just need about 32 ounces of ice, a 32-ounce big gulp cup or something. You throw that in your water bath, and it'll help your bath maintain the 77 degrees and not overrun the temperature. Once the 2-hour period is done, we want to perform the indirect tensile test on the specimens, which is simply breaking the specimens. And they're done one at a time. And we're going to average the set of each 3 subset to get a number with average conditioned tensile strength and an average dry tensile strength, which is a simple division to give us one number for our TSR value. And the minimum TSR value to meet spec is 80%. It's got to be 80 or above. Here's a here's a picture of pine test press. You got a TSR specimen sitting here on top. This looks like that's a 6-inch specimen. Here on the right is the smaller Lotman head. It's the 4-inch specimen. It's just a smaller head if you would be doing it with a Marshall test. All right, and that's actually the end of the TSR test procedure. What I want to give you now is just something a little extra that I recommend you consider. If you notice the multiple days it took for us to do the TSR, that's like a 3 to 4 day process. And if you're ever in production and you start to question if something's going wrong with your stripping or your TSR test, it takes several days to get an answer. What I recommend is when we took our plant mix sample, where TSR samples come from, is that we do one more quick test that provides you as a technician, a mix design technician at your facility, something that gives you a quick indicator if stripping could be a problem in your mix. And that's the old-fashioned boil test. Boil test's been around for a very long time. It was very common during Marshalls before we went to Super Pave. What I would do is when I took my mix, sampled my mix for my TSR, I'd pull out enough mix to run the boil test. Boil test can be used to predict the effectiveness of an antistrip additive. You want to allow your hot sample to cool to 230 degrees. We want to sieve out approximately 800 grams of material. That 800 grams should be of minus half-inch material. Basically, you sieve it over the half. And you only want to do the boil test on the minus half material. The reason is, you don't want, if you're running base, you don't want 1-inch aggregate in the beaker boiling. It'll break the beaker. It's prone to breakage. So we're going to test the minus half material. Once we've done that, we'll screen out 400 grams, separate it in half. We're going to take 1/2 of it and we're going to put 200 grams on a paper towel that has nothing done to it. It's just going to sit there on a paper towel. The other 200 grams will be placed in a beaker and boiled. If you look at the boil test method, it tells you to boil it for 10 minutes. Just give you a little bit of personal experience. I don't think 10 minutes is a long enough indicator. I would recommend you boil it for 20 minutes. If you want to measure the effectiveness of the antistrip additive you use, and this is not a pass-fail test that you're going to have to submit to the department. This is for you to use. This is QC. This is not QA. This is QC for you at your plant. I recommend you boil it for 20 minutes. Okay, during this boiling process, some of the binder will begin to boil off the aggregate. take a paper towel, be careful, put on a pair of gloves and some safety goggles, maybe a face shield, and pull out that binder as it comes off, as it begins to separate from the aggregate. Reason being, when you go to extract your sample from the boiling water, that binder will will sit back on top of the aggregate, and it looks like it didn't boil off. But at the end of that 20 minutes, you dump your sample out on the paper towel, and now you have a nice comparison of a boiled sample versus a sample that has not been boiled. Now, the reason the boil test went away is it doesn't give me a passing number like the TSR does of you got to be 80 or better to meet specification. So it's not a defined number. It becomes a visual inspection, which does put in a bit of opinionated variable into this test. But what it's telling me now, I know that my TSR is passed. So if I have this image, what I would recommend, we all have cell phones or digital cameras now, they're very common this day and age. I would take a digital image of this sample that gives me a boil test that you saw I just performed in like 25 or 30 minutes. That gives me a visual image of what passed my TSR. Now I have that image, I would print it out or save that image for any future testing. Anytime I think something's going on with my TSRs, VDOT's going to come by and take a TSR. Oh no, am I worried my TSR is going to fail? I would know within an hour whether or not I should be worried or not, because I could run this boil test. Just file the image away in a file and you'll have it for comparison sakes. As I said, it's not a required test by VDOT. This is a QC. This is you managing your material the best way you can. And with that, if anybody has any questions, please direct them to your moderator, and good luck. Thank you.